Hey everyone, welcome back to my third video of my calculus playlist, where today we're going to be diving deeper into derivatives. We covered derivatives in my previous video, on my second video of my calculus playlist, but I really only went over the power rule and using limit laws to calculate derivatives. Today we're going to be learning about a lot more different and important laws and theorems to calculate derivatives with more complex functions. So let's start with the basics here with a simple example. Let's say we have the function f of x, like we always do, equal to c. What does that mean? For any input x, we're going to have a constant output of c, right? It is a constant output. Okay, let me just check that. Okay, so we have f of x is c. Again, regardless of what our input x is, we're going to have exactly one output of c. Okay, that's cool. I don't know why this isn't working. Anyways, that's cool. Now, what if I wanted to take the derivative of f of x? In other words, what if I wanted to take d over dx? Oops. Okay. That's weird. I don't know why this is... Alright, anyways. Okay, what if I wanted to take d over dx of f of x? And again, note that f of x is a constant function. It has a constant output. Well, I'll just show you guys right now, the derivative of any constant is equal to 0. But why is that? Why is derivative of a constant equal to 0? Well, let's go back to our constant function, f of x, where we said originally that it was equal to 0. Again, I don't know why I'm not able to control z. Anyways, we know that f of x is equal to 0. So let's use our limit laws to calculate the derivative of f of x. We're going to take the limit as our horizontal distance h approaches 0 of f of x plus h minus f of x, or y1, divided by h. Now, obviously, we can't directly substitute 0 in for h yet, but since we know for all inputs f of x, we're going to have a constant output c. So we know f of x plus h is equal to c, and f of x is also equal to c, right? We have a constant function or a constant output. So that we can simplify this to the limit as h approaches 0 of c minus c over h. Now, we don't even need to plug in 0 for h. C minus c is equal to 0, and 0 divided by anything apart from 0 is equal to 0. That's it. The derivative of a constant is 0. Now, regardless of what the c value is, right, regardless of what that value is, we're going to have the same thing being subtracted from the same constant output in our numerator, which is always going to yield to 0 over something, right? And so for that reason, the derivative of any constant function, any constant, is equal to 0. Okay, that's a simple rule here. Nothing too crazy. Now, I don't know why my control Z isn't working. That's something I'm going to have to work around for today's video, but anyways. Now, so the derivative of a constant is 0, and that's going to be really helpful when we talk about our next more relatively complex rules, right? It's going to be the sum and difference, product, and chain rules. Okay. Let me just make sure I erase every single thing here. All right. Now, let's talk about the sum rule. Let me just highlight that. And I'm going to go step by step here so I can kind of just zoom in here. Okay, you know what? Don't know why that isn't working. Okay, whatever. So, sum rule. Now, I think if I actually... Okay, never mind. So that's not how that works. Okay, it is. Interesting. So, again, kind of just getting used to this new UI. Sorry about that, guys. Feel free to just fast forward this place. Okay, now this is really interesting. Okay, anyways. So now let's talk about the sum rule when taking derivatives of some functions. Okay, so let's start with a very simple example here. Let's say we have the function f of x and it's equal to x squared plus, well, I'm just going to say 3, or rather 3x. How about that? Okay, so notice how this function is simply the sum of two different terms. The first term is x squared, and the second term is 3x. Now, the sum rule essentially states that when we're taking the derivative of such a function, we can simply take the derivative of each term individually and sum up the results. So how is that going to work? Well, the derivative, or d over dx, of x squared individually by itself as a term is equal to 2x. We discussed this last video. It's simply going to be the power rule. Now, what's the derivative of 3x? Now, it turns out we can use the power rule to take the derivative of this as well. Now, if we use this, we'd set 3 times x to the power of 1. If we're taking the derivative of that, we get that this is equal to 3, bring the 1 down, times 1, times x to the power of 1 minus 1. Well, x to the power of 1 minus 1 is equal to x to the power of 0. X to the power of 0 is simply just 1, and so we can kind of just cancel this out. And then we have 3 times 1, which is equal to 3. So the derivative of 3x is going to be equal just to 3. All right, that's good. I'm just applying that power rule. Okay, so d over dx of 3x is equal to 3. Now we can kind of take that back in of our derivative, and so we can state that the derivative of f of x is simply equal to, what did we calculate? 2x plus 3, the derivatives of each of the individual terms. And we just sum up those results. That's pretty straightforward, nothing too crazy. Let's look at another example. Let's say we had f of x. Let me just erase this actually. Okay, let's say we have f of x equal to like some value. In this case, I'm going to say 3x squared plus 10. Alright, so similar approach, we're going to take d over dx of each of these terms individually. That would be the derivative of 3x squared and 10. Now, again, the derivative of a constant is just 0, and the derivative of 3x squared is equal to 3 times 2 and x, which is equal to 6x. And so the derivative of 3x plus 10 is equal to 6x, a pretty simple slope of a tangent line, right? Pretty simple result. Okay, so that's the sum rule here. That's pretty nice when we're taking the derivatives of a function who has a sum of multiple terms. Now, what's the difference rule? Okay, it has a pretty similar approach. Let me just change this to difference. I'm going to say diff for short because I'm not writing out diff with this horrible marker here. Diff rule. Okay. So what does the difference rule state? Well, it's pretty similar to the addition rule or the sum rule, where if we have the difference of multiple terms and we're taking the derivative of that, we can simply just get the derivatives of each term individually, and instead of adding them, we take the difference of them or subtract them. So how does that work? Let's say we have the function f of x equals x cubed minus 5x. Okay, so let's take d over dx of each of these terms again individually. The d over dx of x cubed is simply equal to 3 times x to the power of 3 minus 1. What is x to the power of 3 minus 1? It's simply equal to 2. So this would be equal to 3 times x to the power of 2, which is equal to 3x squared. The derivative of 5x here is going to be equal to 5 times x to the power of 0, which is equal to just 5. And so, bring that up here, we get that the derivative of f of x is equal, let me just write that out, to simply 3x squared minus 5. The difference, using that difference rule, of each of the terms taking each of the derivatives of each term individually, right? That's the beauty of the sum and difference rule. So pretty straightforward examples here, pretty straightforward theorems. What if we had the product of two functions? Okay, that's a little bit more complex. Let's talk about it. Okay, let me just erase this real quick. So yeah, pretty new UI for me as well, kind of just getting used to it. Now let's look at the product rule. Let me actually zoom in a little bit more here. Product rule. I think by zooming in, I'm kind of just showing you guys how bad my handwriting is, at least with a mouse. But it is what it is. So what's the product rule here? Okay, so that essentially says that when we actually have two functions that are being multiplied together, when we take the derivative of that product, we're simply saying that f of x times g of x are two simply functions that we're taking the product of is going to be equal to the derivative of f of x times g of x plus the derivative of g of x times f of x. So it's basically like taking the derivative of the first function times the second original, and the adding of the first function times the derivative of the second. So how does that look with the example? It's a lot better to kind of visualize this with an example using that theorem. So before I actually dive into the example, let me just write out the actual theorem here. So we say that f of x, actually in fact, let me write d over dx first. So we say that d over dx of f of x times g of x is equal to, what did we say before? It's simply equal to the first function times the derivative of the second function. Now, again, multiplication and addition are both commutative. It doesn't really matter how you represent this, but it's important to know that it's simply the derivative of one of the functions times the original function, and the other function's derivative times the other function's regular form. So I'm just going to write it like this. It's simply equal to, again, f of x times the g prime, or the derivative of g of x, plus f prime, or the derivative of f of x times g of x. Okay, so that's the derivative of the product of a function. Now let's take this and apply it to our examples. Let's say we have h of x, and it's equal to f of x times g of x, where f of x and g of x are equal to x squared and, I don't know, let's just say 3x plus 4 respectively. Okay, that was a horrible arrow. I don't know about that. Anyways, so h of x is equal to f of x times g of x, which is equal to x squared times 3x plus 4. So x squared times 3x plus 4. Now let's see this product rule in action. Okay, let me actually zoom out a little bit and move down here. Okay, I don't know why this is not. Okay, interesting. Okay, there it is. Okay, so now we have x squared times 3x plus 4. Let me actually rewrite this a little bit better in parentheses, so it's a little bit easier to visualize each of these separate functions. 3x plus 4. Okay, now first let's just say f of x is equal to x squared, because that's what it's equal to. And now let's calculate the derivative of 3x plus 4. Now 3x plus 4, again using our product rule, is simply equal to the derivative of 3x is 3, and the derivative of any constant is just 4, or rather 0, sorry. So this is going to be equal to just 3. So x squared times 3 as the derivative of g of x, plus, now we want to take the derivative of x squared. We've seen this example a lot. It's simply equal to 2x multiplied by our original function g of x, which in this case we know is equal to 3x plus 4. From here, now that we got the derivatives of these corresponding functions, we simply want to expand and simplify it like we normally do. X squared times 3 is equal to 3x squared. And foiling this out with these two binomials, or rather just binomial or two terms, we get 3x squared times, or rather plus 6x squared, or 2x times 3x, plus 8x. Again, combine like terms of these x squared. This simplifies to 9x squared plus 8x, right? And notice how we kind of just combined our product rule with the sum rule as well. So that's why it's really important to learn all of these different rules. We need to know the sum rule and difference rule to be able to calculate to be able to use the product rule, right? They're all connected in some way when we're taking the derivatives of multiple different complex functions. When there's products, when there's differences, when there's sums, and so on and so forth. Okay, so now that we've covered the product rule, let's move on to the final theorem that we're going to be discussing in this video. That's going to be the chain rule. In fact, instead of erasing all of this, I'm simply going to just zoom out here. Okay, I don't know why. This is kind of on and off for the hand here. Okay, there it is. Okay, let me just move around here. Okay, awesome. Alright. Okay, so now let's talk about our chain rule. I don't know if I should zoom in or zoom out. I think this should be good enough. I might zoom in a little bit. But yeah, that's good. So, in fact, yeah, that should be fine. Okay, what is the chain rule? Well, the chain rule is simply just a concatenation of our product rule and sum rule and difference rule. It's simply just a combination of all of those things. It's one of the most important rules in calculus, especially when you have a composition function, which is defined to be a function inside of another function. Okay, so this rule says, again, going back to our h of x, we say that if h of x is equal to f of x, or rather f of g of x, a composite function. In that case, d over dx, the derivative of h of x, the composite function, is going to be equal to f prime of g of x times, okay, I don't know why this multiplication is weird, anyways, g prime of x. Okay, so what does that really mean? It's a pretty weird looking kind of statement here. Let's kind of simplify using an example. Okay, so we say that the derivative of a composite function is equal to the derivative of f of x times g of x times the derivative of g of x, our second function, inside of our composite f. Okay, let's look at it. Let's say we have h of x, and I'm going to set it equal to, I don't know, I guess 2x plus 3 to the power of 5. Okay, well, so essentially g of x is going to be equal to 2x plus 3. And f of x is going to be equal to, this is a little bit unintuitive. I kind of struggled with this when I first learned calculus, but you'll see how it is. So the g of x is the function inside of this power. It's simply 2x plus 3. But we have a composite function. Why? Because we have a power as another function, right? We're kind of combining or composing 2x plus 3 within this to the 5th power. So f of x is going to be equal to u to the 5th power. It's simply the function of the 5th power, right? Okay, so that's pretty unintuitive. I know. You'll get used to it as you see more composite functions in calculus involving logarithms as well, right? Okay, so what is f prime of u? What is f prime of u? Pretty straightforward. It's simply equal to 5u to the power of 4. Why is that? We're simply applying our power rule in this u to the power of 5th power. So it'd be equal to d over dx of u to the 5th is equal to 5 times u to the 5 minus 1, which is equal to 5 times u to the 4th power. I kind of rushed through that, but that's what it's equal to. Let me erase that now for some more space. Now, you got f, we got the derivative of x. Well, what's the derivative of g? Well, we know that the derivative of 2x is simply equal to 2, and the derivative of a constant 3 is equal to 0. So technically this is going to be 2 plus 0, but we know that that simplifies to 2. So the derivative of f and g of x is equal to 5 times u to the power of 4 and 2 respectively. So now, if we apply this chain rule, we get that f prime of g prime, or rather g of x, times g prime of x is going to simplify to 5 times 2x plus 3 to the power of 4, all multiplied by the derivative of g of x, which is equal to 2. And that is going to be it. Simplifying that, we get that this is equal to 10 times 2 to the power, or 2x plus 3 to the power of 4, which is indeed our derivative of h of x. Rather, it should be pointing here, sorry. Okay, and that is the chain rule for you guys. Okay, so I'm actually going to give you some homework as well for this, because notice how we covered the sum rule, the difference rule, and the chain rule, and the product rule, but we didn't actually cover the quotient rule. That's the operation we kind of missed. Well, it turns out there actually is a quotient rule when we're taking the derivatives of functions or quotients in the field of calculus, and that's the homework I'm going to give you. So, from all this knowledge we gained using these 4 different important rules, where chain rule I would argue is the most important, my homework for you guys is just go online and research what exactly is a quotient rule. When we're taking the derivative of a quotient, so f of x divided by g of x, and we're taking the derivative of this quotient, how do we simplify this? How does this actually simplify? That's the homework for you guys. Feel free to just Google it, research it, see how it simplifies, do some practice problems on your own. I might cover it in my next video, along with the derivative of the natural log, or log base e of x. But that's going to be it for my video. If you guys enjoyed, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.